Buongiorno a tutti. Dico solo due parole. Di solito i nostri colloquia iniziano subito con la parte scientifica, ma oggi è una giornata particolarmente intensa e abbiamo l'onore di avere ai nostri ospiti a questo seminario il magnifico rettore della nostra università, il professor Rizzuto, e il presidente del Consiglio Nazionale delle Ricerche, il professor Inguscio. Sono presenti anche, tra gli altri, i prorettori della ricerca di Padova e di Pisa. Sappiamo che le tecnologie quantistiche sono una delle grandi frontiere, delle grandi sfide del futuro, e quello che speriamo, il nostro Dipartimento vuole investire molto in questo, e quello che speriamo è che da oggi possano partire nuove forti collaborazioni. Ok, lascio subito la parola alla parte scientifica e l'introduzione sarà fatta dal professor Marchetti, che è il nostro docente di meccanica quantistica e che è stato anche il docente di Tommaso Calarco quando era studente a Padova. Ok.
Inglese, okay. So it is a particularly great pleasure to have as speaker of this colloquium Tommaso Calarco, now coordinator of the €1 billion project of the European Community on innovative quantum technology named Quantum Flagship. Since Calarco started his career, as has been remarked now, in physics precisely as a student of this department. Later he got his PhD in Ferrara, and after a research position in Innsbruck, Trento and Harvard, became full professor in Ulm, and there within few years director of the Institute of Complex Systems and the Center for Integrated Quantum Science and Technology, and now is professor in Cologne and director of the Institute of Quantum Control in Jülich. He has authored in 2016 the Quantum Manifesto, which is initiated the Quantum Flagship initiative, and currently is the chairman of its Quantum Community Network. Tommaso Calarco's research interests include quantum and atom optics, quantum control, and quantum information. In particular, he was a pioneer in the application of quantum optimal control methods to quantum computation and to medic-body quantum systems. The title of the colloquium, which is not yet there, but is the world's fattest Schrödinger cat. So let me just say that the Schrödinger cat is a strange cat, which is in a sense simultaneously dead and alive due to two astonishing properties of quantum systems. The first is the superposition principle that allows a system to have at the same time, potentially, two properties that in our classical world are mutually exclusive, like dead and alive. The second property is entanglement, that allows the reality of two components of a quantum system, in this case the quantum particle that trigger the mechanism that kill or not the cat and the cat itself, to be deeply connected without physical interaction. None of the two components having an independent reality, which is, for us, is really amazing. But it's a key of quantum technology. So from the world of the Gedanken experiment of the early times of quantum mechanics, the Schrödinger cat has become, in a technological incarnation, a star in the present era of the so-called quantum revolution, second quantum revolution, involved in the development of quantum technologies, of which Calarco is a leading feature, that we have the very interesting opportunity to hear now.
Thank you. Well, thank you. It's really, for me, a moment which is, as you can imagine, full of many emotions here. I was essentially not in this room since, I guess, 25 years. And it's also very emotional for me to give this talk today in front of some people who, without whom I would not be here today giving this talk. And of course, the first one is Pier Alberto Marchetti, who taught me quantum mechanics, many years ago. And another one, also belonging to this university, is Roberto Onofrio, who more than 25 years ago believed in me doing some completely useless stuff for my master thesis. And at that time, it was completely useless. It was almost purely philosophical. It was Bell inequalities. And they really remarkable thing is that nowadays we use these things, we use superposition entanglement for technological purposes. And the third person I would like to mention, last but not least, is of course Simone Montangero, who has very strongly contributed to inventing a lot of the ideas that I will present here when he was with me at the University of Ulm. And so what I would like to do is to both provide some insight into the research that we are doing, and also a little bit, since there are some very distinguished guests today, as our director has mentioned, I would like also to give a little bit of a view what is this big initiative that we have at European level, because this might lead to some very exciting developments also in Italy in general, and especially here in Padua and in the region around. So I would like to start by saying what quantum technologies are. Well, of course, what many of you have in their pocket is quantum technology. So without mastering the laws of quantum mechanics, it is completely impossible to create a processor to process information in the digital era, to send information across the internet. So as I like to say when I explain this to politicians, yesterday night I gave a talk in the German parliament. I told them without quantum mechanics, you would have no Facebook, no Twitter, which maybe would not be so bad after all, but certainly it shows us that quantum technologies of the first generation, they are really impacting our life every day. What is the point of the second generation? Well, in the first quantum revolution, what we have is essentially we can understand and predict quantum devices and systems, and we have for our bits many photons, many electrons, many atoms all together, but they are many, so they behave classically. Per bit, I have many electrons in an integrated circuit. I have many photons on an optical fiber. Now, what happens when I go to the second quantum revolution? This is where we are really dealing with these things at the individual level. And we can engineer their properties, and this enables us to get technological applications which have more computing power, more sensitivity for sensor, more security, more speed for computing. And this is the basis of this initiative that we are having at European level. So there are different application areas here. And all they come from manipulating individual quantum systems. So why is that? Because, for instance, if we manipulate individual atoms, we can go beyond the precision of current present-day atomic clocks. So if we manipulate individual atoms and we exploit properties such as entanglement, we are able to enhance the sensitivity of those atomic clocks, and those are necessary, for instance, for satellite navigation, which means that if we can improve the precision of time measurement by a couple of orders of magnitude, we can know the position of our car, not within a few meters, but within maybe a few centimeters or even millimeters. And this has, of course, a lot of implications for society, for instance, for autonomous driving. But then, of course, if we use individual electrons, electrons are, of course, the smallest magnet, if you wish, that exist. The individual spin is the tiniest magnetic moment that you can have. So if you have a very tiny magnetic field, then an electron can sense it. And actually this has been used, for instance, to measure activity, like on and off switching, firing of individual neurons in real time. And this may seem, well, a few years ago it was almost science fiction. And now in Germany, we have a pilot project of our national program on quantum technologies in which the company Bosch is creating a helmet which you can equip with tiny nanodiamond-based quantum sensors. I will come back to that afterwards. And you can use this to start reading brain function in the direction of creating a human-machine interface. So this is not just something which scientists in some crazy, fundamental, useless lab, just curiosity-driven, are doing, but it's something which industry is investing strongly nowadays. And of course, this has implications for medical imaging and for a lot of developing science, but also, for instance, for therapy, for enabling patients which cannot communicate with the external world to perhaps be able to communicate again. Now, another point which you can get, if now you use another kind of individual system, individual photons. So a photon, of course, is a quantum. You know it. You cannot split it in parts. So what is the difference if I transmit bits for instance, a cryptographic key via quantum channels? Nowadays, as we know, the NSA can come and take a few photons per bit that we transmit, and then, the Americans know all that we are discussing over the internet in principle. And this is something which, the society has learned with a certain level of surprise. Of course, we always knew that this is the case. Of course, there is some complexity in cryptography, but this can be broken with sufficiently powerful computers, and in the future also with quantum computers. But now, if you, per bit of your cryptographic key, you transmit one photon, that cannot be split. You cannot take one part of it. So if the NSA comes and they try to take it away, well, you will notice it. If I send you one photon at a time per bit, and you don't get it, then you know that someone has tampered with the channel. And if you get it, we can verify that the state is the correct one, and then we are sure that no one has tampered. We know that we have a secure communication channel. So individual photons, secure communication. Now, what about computing? And you might have heard in the press in the last few weeks, there has been this very important breakthrough from Google, which created a 53-qubit quantum computer, which performed in 3 minutes a calculation which the most powerful supercomputer on Earth would take 10,000 years to complete. The little issue is that it was a completely useless problem, okay? It was a completely academic, futile problem. Again, it shows that, fundamental research is the foundation for all of this. Because the next step, and quantum computing is based on using individual atoms or ions or superconducting circuits to encode qubits, to use entanglement to process information in a parallel fashion, then it means that if we can get the proper algorithms for this, we will be able to have much bigger computing power for a lot of problems, also of practical use. Volkswagen, 1.5 years ago, used a quantum simulator, a specific version of a quantum simulator, which is a quantum annealer from a Canadian company, D-Wave, to optimize the routing of taxi cabs in Beijing. And this is something which, to a physicist, would never occur even under a very heavy influx of vodka. Which shows that it is good that we start these things, but it is also good that somehow they are taken out of our hands and also shared with computer scientists. For instance, we had this conversation earlier with people in industry to really devise new application fields for these enormously powerful tools. And we are just starting on that. Another area which is, again, relevant beyond this medical imaging that I mentioned before is using individual systems at quantum level for sensing, for measuring tiny variations in the gravitational field, for geoprospection, for instance, I was 2 days ago with an Australian colleague who explained that in Australia they want to use this from a satellite to measure the level of water in the ground, because depending on how much water you have in the ground, then there are tiny changes in the surface of the Earth, and you can measure that with a quantum sensor on a satellite. And in Europe, we are already working in this direction. The German Aerospace Agency is putting such quantum sensors, cold atoms, BECs, on satellites. And of course, last but not least, I'm saying this because, for instance, Simone Montangero is one of the leading figures in this field of quantum simulation. He's coordinating one project within the flagship on quantum simulation of lattice gauge field theories, something which is relevant for high energy physics. With quantum simulators, again, you use individual atoms and you put them in some periodic structure, and then you are able to reproduce properties of some other physical system as a specific case of very powerful computing machine. So there is a range of applications. It's not just quantum computing, which is maybe due to the strong Google propaganda often in the foreground in the press, but it's a range of different applications. And based on this flagship initiative has the goal to really bring these ideas out of the lab into industry in order to really make Europe great again, one would say. No, one would rather not say that, but make Europe a dynamic region. We lost the train of the internet revolution, it was invented in Europe, it was invented in Geneva at CERN, okay? And I'm saying this because I know that in this department, the tradition of high energy physics has been and is very strong. The web was invented there, and essentially all the earnings were made elsewhere. So we want to change this. The European Commission recognized this in time, and so there is an investment in order to enable this revolution to come to Europe. And here are some numbers from the first round of projects. There were, more than 140 proposals. 20 have been selected. We have 150 millions for the first 3 years, which are now being distributed. And we are talking with the European Commission. So in the European Parliament, they accepted with the function Control-C, Control-V, they adopted a little piece of text, which I sent to them, which now is in the legal basis of Horizon Europe, the next framework program, in which I was proposing that for the contribution from the European Commission would be 3 times as much as was proposed in the beginning. So now we are talking between 2 and 3 billions altogether. So, well, this is kind of promising, but as I said before, it relies on a broad span between fundamental science, and here we not only have the quantum flagship, but also Quantera, which is one consortium of national funding agencies which put together the resources, and here is one of the projects which Simone Montangero, my colleague here, is coordinating. And this goes all the way from research, which is in this program Horizon Europe, all the way to digital Europe, which is maybe less familiar to many of us, but here is where we are going to plan infrastructures. What does it mean? It means that on quantum communications, the European Commission is planning to create secure quantum links across all European capitals. This again may seem science fiction, but in China, the Chinese have already done it 2 years ago. They have a secure quantum challenge between Beijing and Shanghai, and they also put it on a satellite, because the first teleportation experiment was done 20 years ago in Innsbruck, and the first author of that, so the last author, the professor, was a guy named Anton Zeilinger, and the first author was named Jan Wei Pan, which is not exactly Tyrolean, as you can guess. So he went back to his home country, he got from President Xi $2 billion, and he put this technology on a satellite, and now the Chinese are ahead of us in terms of implementation. In terms of know-how, Europe is still very strong, and actually here in Padua, there is my colleague Paolo Villoresi, who is one of the protagonists in this research on quantum communication on satellites. And then down the line, so here is maybe the part which is most relevant to some conversations that are taking place also today, is the quantum computing infrastructure, where we are going to take the first prototypes with 10, 20, 50 qubits of those quantum computers, which are being produced by the flagship, and deploying them next to existing supercomputers. And not far from here, in Sineca, there is one of the 3 sites which have been chosen for the pre-exascale, the next generation high-performance computing infrastructure in Europe, and we are just working on plugging as hybrid co-processors, some quantum processors in that structure. So this is bringing us, well, to the last 2 slides of, let's say, this broad non-science, but maybe more policy kind of introduction. One is, what are the goals of this quantum communication infrastructure? As I said, we want to integrate those single photons into normal communication systems. We cannot replace the whole internet with that. As of now, the goal is, in the long term, to create a backbone for enabling that, both with the terrestrial and with satellite links, okay? And then this will be something which will be the basis for a future quantum internet. And this, of course, has a lot of implications for data security, but also for synchronization of clocks, and a lot of other applications in metrology, and so on. And then, maybe most relevant, perhaps, to the current discussions that are taking place here is the quantum computing and simulation infrastructure. As I mentioned, this involves not only having, quantum hardware being, integrated in existing high-performance computers, but also a lot of classical software and computer science applied to quantum computers in order to be able to find the proper use cases. Because at the moment, what Google did is a historic moment, but it is like the Wright brothers flight. It flew for 12 meters. It's completely useless, something that can fly for 12 meters. but everybody now can appreciate what was the impact of that. So Google's machine calculated something which no one can really use for something of broad interest, but it shows that it is possible. It broke down the Church-Turing thesis, one of the foundations of classical computer science. Since 3 weeks ago, it is no longer valid. So this is really a major milestone, but we have to go a lot further in order to enable real applications, and this is where the physicists are not sufficient alone, and so this is why we are having a broad interdisciplinary discussion here. And, well, this is why I am also very happy to see that so many distinguished guests have converged for such discussions here today, because this can bring a lot of advantages, including to your university. So now I would like to focus down a little bit. So I mentioned that we have several projects, of the order of 20 projects. They are distributed in those areas that I mentioned before: communication, simulation, sensing, computing, and also basic science, which still is the foundation of everything. And what I want to focus on is some ideas that I am developing in the context, in particular, of simulation and sensing, with the 2 European projects in which, again, Simone Montangiero is involved, in particular in the PASQUANS project, this one on quantum simulation. So I want to tell you some ideas that we have developed, how you can make those simulators and sensors better. So what I'm going now in this more scientific part of my talk to describe is how you can control those quantum systems to make them perform these relevant tasks. So you want to control quantum dynamics, and there are methods from optimal control. I will explain what that is, and also I will describe the method that Simone invented back in Ulm 10 years ago, which is the only one which works with many-body systems. I will explain that in a moment. Then I will show how you can apply this, and there is one approach which is the plug and pray approach, like you plug the algorithm, then you go to some Madonna, or maybe Sant'Antonio is also possible in this town, and you light some candle and you hope it works. Or, you could also do the closed loop, in which you are sure that it works because you are sort of embedding it in some automatic calibration. And at the end, I will bring all these ingredients together and show you how we realized, together with colleagues in Harvard, the fattest Schrödinger cat that mankind has ever created. So, how does it work? How can you control quantum processes? Now, here comes my favorite example of controlling a non-trivial process. So, we have today, someone who is chairing the session, okay? And he told me, well, you have more or less 45 minutes to speak. But, I have many important things to tell you. So, I would like to speak for 3 hours. I must make sure that the director will not realize at the end of the 45 minutes that the time is up. How do I do that? Well, fortunately, behind here, you cannot see. Oh, actually, you can see it. I will not open it for you, but here there is a tap, which, under proper conditions, is emitting some pleasant fluid, which has some alcoholic content, which I can put on a tray. I can fill all my glasses with champagne, and if I deliver them in the right state to Professor Seno, he will enjoy that and not realize anymore which time it is. So I have this very well-prepared initial state. I have to deliver that in proper, conditions over there. Right temperature and maximize, this is the optimization problem, the amount of alcohol that he will get. So how do I do that? Of course, I do not want to spill my alcohol, right? Otherwise, I do not optimize. So I will do an adiabatic process, which is like this, okay? So I will not have any excitation in my system, and I am sure that I always stay in the local ground state, and at some point I will get there, but it will take some long time. So when I deliver my state there, well, there is also interaction with the environment. It is a thermal environment, which implies that, he will not like it, because, who drinks champagne at 20-something degrees? So I had to try again, right? So I say, well, it took too much time, so big T time was too long. Let me try again. So I have a certain time dependence, certain big time T, some linear time dependence. So I will say, okay, let me do it quicker. Okay, so I go like this. But before I am halfway, 50% of my road, my path, well, actually also my fidelity, so the quality of the process has dropped to 50% in the sense that half of the glasses are on the floor. And so I deliver some of them in the right temperature, but it is not sufficient to achieve my goal. So I fail miserably. I have to try again. Well, fortunately, I am a professor in quantum physics, so I'm a learning system in particular, and so I can take private lessons from a waiter. I can try again. And of course, first time it doesn't work, but if I retry, it could improve. And if I observe what a real waiter is doing, what they are doing is, well, a little bit more sophisticated because they have some excitation in the beginning, and then they accelerate, and then they de-excite, and they serve. And so what happens is that the initial and the final state are the ground state, but I have some non-adiabatic excitation. And of course, I have to do it in the proper way to get down to the ground state at the end. But if I do that, I can achieve it in a way which is maybe non-typical. Okay, this is not a typical physical process. Well, actually, I have to really be able to anticipate what is the behavior, the dynamics of my system. But if I can do that, then I can, as I said, accelerate it. So this is pre-Photoshop, Alfred Eisenstadt, famous photographer, St. Moritz, 1941. So this is not deep fake. Okay, so it's a real physical device. And if I told you this without exhibiting an example of a physical process, you would say, that's not really a typical physical process, right? But nevertheless, it works. You can adjust things such that it really works. Of course, you have to use all your control parameters. You have to tilt the tray, and you have to do it in a proper way. You could do it sequentially, like I start like this. I tilt the tray, then I move on, okay? And then I untilt it. Not very efficient. But if you combine your time dependence in the right way, then you can make some more interesting things. And so this is what we are going to describe in the quantum domain. Now, what is the intuitive picture here? I have some energy levels. That's a quantum system. I have some time dependence. And let's say that this is maybe depicting a many-body system. And I start in a certain phase. Of course, this is not really in the thermodynamic limit because I have a gap here in between which is not yet closing. But I start from a certain many-body state and I want to go to another one. I can go adiabatically, like my first attempt. I can go slowly. So I stay close to the ground state. And it means that, maybe with a little error, I will end up where I want to be. Now, if I try to do it in a shorter time, well, I shrink the time here. But of course, there is a problem, because if I just do it naively, I will cross unavoided crossing here, so I have excitation in my system. And so, well, I'm not reaching my goal. But what I can do with optimal control is essentially I do more excitation in the beginning, and then it converges down to what I wanted by virtue of quantum interference. And so this seems very strange, but it does work. And I want to show you that it works. Well, first, theoretically. So here, let's say that I want to transport something which is more interesting for quantum information. It could be a quantum state. It could be a quantum bit. So I have a chain of spins. And then I have a certain quantum bit state on one end, alpha 0 plus beta 1, generic superposition. I want to transport it to the other side. Why is this relevant? Because maybe, and this is actually a problem which Google has at the moment, how do you engineer the system so that you get bits across? Well, you can have a wave function on one side, you move it around, and you can do this with some model which was proposed almost 20 years ago, and it works like this. You have some spin Hamiltonian with spin-spin next neighbor interaction, and you have a certain external field. And this external field is not homogeneous. Next to the minimum of this field, you are able to have spins which can flip. So if you move the minimum, you will, transport this step by step, the excitation up to the other side. You may be able to do it also quickly. Let's see how it works. So first, step by step, adiabatically, one after the other. And here is when I move my spin population, all of it from one side to the next one. But now if I try to do it more quickly, then what happens is that, I leave some of the champagne on the floor. So these Landau-Zener crossings imply that here there is some population which is left behind, and not all the population is coming where I want it. So how do I solve it? And now comes the most important theorem in physics. It is valid for theoretical and experimental physics. Given any problem in theoretical or experimental physics, there exists a Russian who solved it 40 years ago. And a relative, friend, or descendant of that particular Russian will stand up during your talk and claim, we do this in school. Yes. And the sad part is that they are right. It is a fact of life, okay? So you just have to find, so the only thing that changes is the name of the Russian, okay? In this case, the name is Grotov, Okay? So here comes the Krotov algorithm. And existence of Professor Krotov was demonstrated by phone call I received after giving this first part of talk in front of 15 million viewers on Russian television, no joke. And he called me and thanked me for advertisement. So he does exist. Yes. So, and how does it work? It works that you have an initial state. You want to evolve it with some time-dependent control. You get to some final state at big time t. And then you are there, and some of your glasses are on the floor. You have some error, and then you say, oh my goodness, what should I have done differently? Like you project, you start counting what went wrong, and you go backwards, and you say, what could I have changed to get a better result? And there is a systematic way to update, to change the time dependence in order to get a better result. It's a functional of the Hamiltonian and the forward and backward evolved state. And in the particular case of Krotov's algorithm, what you do is you iterate something which is actually a gradient of the Hamiltonian with respect to the control parameter, mathematical trick, similar to Lagrange multipliers, and it works. It's guaranteed to converge. So let's see what happens if instead of this flat, simple linear dependence on time, you use this algorithm and you update the pulse. As you iterate the algorithm, you see you develop some kick and counter kick in your time dependence, such that when you go and look at what the system is doing, well, it's juggling the spin population around, creating a sort of moving soliton, and then it catches it back in a time which is more than 2 orders of magnitude faster than if you didn't use this, and still with very high fidelity. So now, you say, you're a theorist, you say, I have a great idea, I have a great method. What do? You go very excited to your experimentalist friend. And what does the experimentalist friend do? That's also a known fact. They will complain. They will say, oh, no, it doesn't work. Oh, no, this is too ideal. Oh, no. I mean, you know, in my experiment, I have imperfections. It is impossible that it works like this. So you spend the rest of your career to convincing your experimental friends that it can work, okay? And in doing that, you have to develop some better methods. So here is our alternative method to the Russian method. So we made a little mistake here, okay? Because, well, all of us, as you can see, who are on this first paper, are Italians. So, but we didn't realize that we were in Germany. And not all of my German colleagues will pronounce the acronym of this beautiful algorithm in the correct way. And therefore, ladies and gentlemen, I give you the RedCRAB algorithm. So, it works in the sense that, well, I have a certain pulse shape, and then what do? I want to update this pulse shape, and how do I do that? Well, I put an update function which is just a function of a few basis functions, a few sinusoidal or polynomials or different functions which are appropriate for that particular system. So you reduce the dimensionality of the problem. When you update the pulse, then you have only a search in a space which depends on a few parameters. So if you depict it visually, what you have is, you know, in this case with 2 parameters, you have a function which is a function of 2 parameters, and you start in some place up there, and you want to go to where this function has a minimum, and you can let this triangle roll down. This is the simplest way. It's actually a Simplex algorithm. You get a pulse shape which has a certain spectral properties which correspond to what your experimental friend can do. So then maybe they are convinced and they will try it. And then in doing this, you do not need a gradient. You do not need any other trick. It's very, very simple and robust. And so it can be used in what I described before as the plug-and-pray approach. So let's come back to what I mentioned before. Those individual electrons which behave coherently in color centers in diamond at room temperature. And you can use them to do some magnetometry. And here is a few level Hamiltonian, which you can manipulate. And what we want to do is to manipulate this using our method, in this case with sinusoidal functions. And we do this in a way that we take into account that our system down here is just not getting the pulse that we synthesize, but also there is a waveform generator, there is an amplifier, so the pulse that the system gets is distorted, is not exactly what you wanted it to have. But you can incorporate all of this and calculate some quantum operation, some rotation in this 2-level system, a pi rotation, a pi half rotation, and then they measure it across the whole way, because this was done in the Institute of Fyodor Yeletsko, who is one of the protagonists in this field of nanodiamond magnetometry, who also is in Ulm. And this is the result that they get, so which is going essentially on top of what we predicted. And if you don't use optimal control, like if you, on this block sphere, you go from top to bottom just on a straight line, what happens is that you are populating other levels because this is too fast, for it's not adiabatic, okay? So it would be too fast, and then you would excite and get a fidelity of maybe 15%. So you would get 85% error as opposed to maybe 1% error. So this is working, it's promising, and now you would like to close the loop. So what you want, I mean, for operating this, you need an optical table and a student, okay? So, of course, you cannot do without optical table, but you would like to do without student. Or at least you might want to allow the student to go to sleep during the night. So, the student comes at night, they switch on the experiment, they go home, they enjoy coffee, something else, they come back in the morning, and the fidelity goes from 50%, so 50-50 chance of getting it, to 100% within the experimental error. This is what you would like to have. So we have to try to develop an approach for that. So first, of course, there would be a numerical simulation, which is getting the best paths that you can have, and then you go in a closed loop, like you measure your system, you do an experiment, it gives you some figure of merit, and then you go on iterating this. But when you do this, you remember this green picture, this landscape? Well, the one I showed had just one nice global minimum, but it could have local minima. If I get stuck in a local minimum, how do I get out of that? Well, so here is where we developed ideas to go out of those local traps in what is known as the control landscape. So let's say if I have one minimum or maximum, no problem. If I have two of them, well, then I could get stuck. What do we do? Well, actually, this landscape, as I said before, depends on the fact that I have a few parameters in there. So if I change parameters, I will get a different landscape. What do I do? Now I use the fact that this RedCRAB algorithm has an R in there. It's a random basis, meaning that in my, for instance, Fourier components here, I have a random component in the frequency. So when I get stuck in a local minimum, what do? I throw away one of the components, and then I replace it with another one just by random, and in most cases, I am mathematically guaranteed that the landscape will change, and from having something complicated with local minimum, I get to something where the local minimum disappears. So I unlock this trap, this is what we call landscape engineering, and then we proceed further downhill. So let's see how it works for this diamond experiment I showed before. I have a certain laser pulse, I have my diamond system, I measure some fidelity, and then I apply my control. This time is called the DCRAB, dressed CRAB, in the sense that it is this evolved version, and I will produce something which is automatically synthesized by the system. So how does it work? Well, here we go. We want to realize a Hadamard gate, which is going from, it's half a pi rotation, going from a 0 state to a 0 plus 1 state in our qubit. We start even with a random guess. So not even pre-optimized, but just we throw something, and in the beginning it will have 50% chance to work. And you see here, at night, when you switch it on, it's 50%. Then after a few hours, these are real hours, of the experiment running, then the fidelity goes up, and you get up to 100% within the experimental error. And so this is something which you can use as a firmware for your quantum device in order to enable it to reach automatically calibration, even in the presence of drift. Like if the system is changing its behavior during the 6 hours, you can still, go and fit into the optimum. And here is to show that, well, if you compare with a normal, like a square pulse, which you would do naively, which would not work, would have, as I said, maybe 10-15% fidelity, then you get this black line. And this is, it's not a crazy shape. It's something which the system can do and is synthesized by the system for the system. So, well, until now, we did something which, was done better, maybe, or faster, but that you would anyway be able to do. But we would like to go towards something which otherwise is impossible. For instance, beating the world record on an entangled state. So, well, we realized that this new algorithm works also on the cloud, in the sense that I can have my algorithm sitting in the lab, or it could be elsewhere, And this loop of measuring and updating the pulse shape goes over some internet connection. So this is what we call remote DCRAB, RedCRAB, and we wanted to test it in a real experiment. So we used what is known as quantum games. So there is a website in Denmark. It's called scienceathome.org. You can go there with your computer or with your mobile phone. And there you are presented with a nice transport problem of a wave function. And with your finger, you can move your potential from left to right across obstacles and so on and so forth. And you would say, who is so completely nuts to play this game? And the fact is that this game has been played by thousands of people, hundreds of thousands of times. And so these researchers in Denmark, they have the purpose of doing what they call citizen science, to see what can come out, okay, if you have real people trying to solve these problems. And for us, what was important was to try and use our algorithm in order to compete with people. So, because people, I should say, were able to beat the Russian algorithm, but they were not able to beat ours. Let me show that. So here is how it goes. This is a video to explain the experiment to just gamers. And so you have a certain fluid, which is high temperature. In this case, it is about creating a Bose-Einstein condensate. So you wanted to create it in an optical trap, and you pour or maybe drop your liquid into the trap. And then as you lower the depth of your potential, then what happens is that at some point it gets very cold, okay? So maybe it is not working like this for coffee, but in a real experiment like this, it will work that you transfer your system into this magneto-optical trap, and then you start trapping with laser fields, and then what the players can do is to change the shape, the time dependence. In this case, is some exponential, it's not sinusoids. They can change the time dependence of the lasers in order to achieve the best score, and the best score is how many atoms you have in your Bose-Einstein condensate. So they played this, and we did it as well, over the internet, and here is the result. Well, fortunately, I should say, so the dashed line is what the best result was of regular people, including performing better than the Russian Krotov algorithm, and the red line is proudly our CRAB method, which goes not so much beyond that, but still, achieves the optimal result. And for us, the most important part really was not creating a Bose-Einstein condensate, but showing that it can work over the internet. So now I can come to the last few slides of the talk, in which I am bringing, as I said in the beginning, all these different ingredients together in order to do what? To create something which was never done before. The previous record was 14 qubits in the lab of Rainer Blatt with trapped ions, which were put in a GHZ state, a Grünberger-Horn-Zeilinger state, which means all ions in the 0 state plus all ions in the 1 state. We wanted to go beyond that. We used the RedCRAB. Here's what comes out. So what I showed you before, the level scheme I showed you before was just a cartoon. Here's the real level scheme of those Rydberg atoms, which are trapped in an array of optical tweezers here. And you can put them 1 atom per tweezer, per potential well. So you have a nice array of atoms. The level scheme is down here. And you can sweep some detuning the frequency of the laser field, which is addressing that, in such a way that you go from a state with all of them in state 0 to a superposition, 0, 1, 0, 1, 0, 1, plus 1, 0, 1, 0, 1, 0, and you try that with increasing number of atoms. So here's the result. With 20, we see that the only states which are populated are those states that indeed we wanted. There is some statistical correction to the results here in order to get from the raw data to a real estimate of the quantum state. Here is the actual pulse shape that was synthesized by our system. Here is some parity oscillation, because of course it is not sufficient to say, okay, I have either of the 2 states, but I want to see that I have coherence, so that these 2 states are in a coherent superposition. You can rotate them and then do some interferometric measurements such that you get these oscillations, which give you, so the visibility of these fringes is telling you what is the fidelity of the entangled state, which is 54% more than 54%, this is the lower bound for 20 qubits. And here it goes. Of course, the visibility goes down as the number of qubits increases, so the fidelity of the entanglement goes down. But here's the important part. So if we try without optimal control, then we can get, a good entangled state down to, up to a certain number of qubits comparable to what was done before. If you want to go beyond, then only, so the point down here is without optimization, the point up here is with optimization, and the yellow one is the one including experimental errors, which in the end is the result of this very complex experiment at the limit of what is possible. Actually, I was very frustrated last summer when we were about to publish this, because I was sitting next at a conference in Rome next to the head of the IBM quantum computing lab, and I told him, I have a cut of 20 qubits, and he said, oh yes, I have one too. And I said, oh my goodness. And they were going to publish it, and then they published it, but theirs was 18. So ours is bigger. So I want to underscore, it's not just, this optimization is really that we are using the many body dynamics and many body excitations in the system in order to achieve the goal. And you can see it here, because here we show for increasing numbers of atoms, and this is my last slide. You can see that the population in the ground state is less than 1 during the process. Like before, you have an excitation, In the beginning, ground state, in the end, ground state, but during the process, you have some excitation. And here you see it. If you didn't have excitations, you would have this line completely flat up to 1. But you see, as I increase the number of atoms, then I get more excitations, more and more excitations, because I really need that quantum dynamics in order to get to my goal. So what I hope in my summary is that I was able to convince you that indeed optimal control works. It works with the RedCRAB method, and it not only works for simple few body systems, but also for many body systems. Only algorithm which does that, and actually not only in theory, because as we know, in theory and practice are the same, but in practice they aren't. And so, in this case, we show that also experiments work. We can do it as a cloud service. We can beat the world record of the fattest Schrödinger cat that mankind has ever created. And actually, we are going to offer this as a cloud service. We have plans to create a startup to offer this as a firmware, software, built-in component for quantum devices. And with this, my time is up. So thank you very much for your attention.
So thank you very much for this bright vision of the future. And now if there are questions, please.
So nowadays there are many methods for minimization, also thanks to the fact that artificial intelligence is interested in minimizing costs and so. So are you not using these methods with a reason, or you use this gradient-less method because it's better?
So we have used it. We have used it because it was the simplest, because it was until now the most efficient to get to the result in robust terms. But as the complexity of the problems we are dealing with is increasing, for instance, for the Schrödinger cat, the next generation that we want to do with Harvard, we need to be more resistant to noise. Okay, you saw a discrepancy between what we had calculated and the actual measurement result. And indeed, we believe that this can be achieved with machine learning techniques. And in my Institute for Quantum Control, which I founded in Jülich, where I moved, as Professor Marchetti said before, 1 year ago, I just hired a couple of people with specific expertise in machine learning applied to optimal control precisely to go in that direction. This is one of the new features we want to include in this software that we are planning now. So this is a very central current research problem for us.
In the graph which we show your numbers versus experiment was going down and you're saturated. Can you explain?
Yes. So yeah, this one, right? Yes. So the fact is that in this case, okay? In the end, we did it over the cloud, but so it was a closed loop, but it was not a closed loop with their experiment for the large numbers because it would take too long to get the iterations. So in the end, for the large numbers, it was a closed loop with their own simulation of the system. So it didn't take into account all the possible errors in the system. So it was expected to have a degradation between the calculated result and the measured result. And actually, one of the improvements we want to achieve, when I mentioned in the previous reply, the fact that we want to get machine learning methods to be more sensitive to noise, is that this will enable us to do closed loop also in that case. And so in this case, there will be no longer a discrepancy between the optimized and the measured result because they will be automatically the same.
So let me ask, for the quantum computer, which is the practical realization that, which is the way in which you practically want to build a more efficient quantum computer? There is
yes.
idea?
So actually, one of the ways is this one. So with neutral atoms, actually, in this project in which we both Simone and myself are participating, the idea is really to use these Rydberg atoms, so highly excited Rydberg atoms, neutral atoms, which are trapped in optical fields by an array of optical tweezers, and you can first you populate in a random way somehow these traps, but then you can regroup them in such a way that you have one per lattice site, and they interact and they get entangled via dipole-dipole interaction in these Rydberg excited states, and this is state dependent, so you can get entanglement due to the state dependent dynamics which you excite like that. And this is one approach which is especially useful for quantum simulation. For quantum computing, the two mainstream approaches that are being pursued now, one is the one with superconducting qubits, in which Google is now world leading, but also IBM is very close to that. Intel is also working on this, and we have a project in Europe based on superconducting circuits, which interestingly is really the system which I was working in my master thesis with Roberto Onofrio for these Bell's inequalities, and this is really the connection that these systems, it was a double well potential, and now this double well potential, you call the first well 0, the other 1, and then this forms a qubit. So this is really the immediate connection between this fundamental and the very applied side. And the other big component here, the other big candidate is ion traps. So in linear electromagnetic traps, you can trap a chain of ions, and then you can couple them via the common motion of the oscillation induced by the Coulomb interaction, and this is the way in which you entangle them. And with this, for instance, Rainer Blatt in Innsbruck, who had the previous world record for the largest GHZ state, he was able now to use 20 of these ions to perform a quantum simulation of some aspects of high energy, so lattice gauge field theories. So those are the main. There are other approaches also. Diamonds can be used, but those are the main ones which are currently being researched.
This is a more a complex question, maybe. The preparation of students, of young generation of students that want to get into this very exciting field, how are the Germans and the other countries you're familiar with, how do they organize the training of the students, and how, in your opinion, is the Italian system in a good condition to be able to put students into this field?
So the Italian system is inexplicably amazing because it is a fact, which is a known fact throughout Europe, that despite the constant cuts which are invariant by rotations of the constitutional axis, which are performed onto the university system, the quality of Italian students is always amazing, and if you can just snatch one, you certainly do, okay? So this is really something which no one can explain. Some of my colleagues say, this country is so beautiful that we don't need so much money for everything to work, but I do not really believe there must be a reason which no one can explain, okay? It cannot just be the excellence of the school, the tradition here. I don't know. But it is a fact that Italian students are very, very coveted as postdocs in this field everywhere and very successful. What other countries, and maybe this is because, I don't know, because if I compare with Germany, for instance, in Germany, in the university, you have to take your students by hand, okay? And it's almost like in the high school, and if you do something which was not exactly in the same form in the lecture, they get very upset, and you should not do that. So somehow Italian students get more autonomous because I don't know, the system is more healthy, I would say, in this sense. Specifically on, and this is a general statement, specifically on quantum, actually, what we are trying to do is to create specialized courses for quantum technologies and quantum engineering, both PhD courses, and of course, there is an important initiative also in this country on this. Francesco Cataliotti, who is here, is one of the protagonists in creating that, you know, and of course, this is something which is, as well as many other things, an aspect in which the CNR has a very leading role, I would say the main role in this country in this moment. In other countries, we are also trying to move in this direction. There is an idea at European level to really create curricula in this sense. The European Commission has just concluded a call for a preparatory action to really create master's programs. And why masters? This is a conversation we had before, because many companies are creating these groups and they need people who are trained, and this is missing. So this is really the focus for the European Commission. And again, the National Research Council in Italy has the lead in this coordination action, which is in this case taken up by a colleague in Pavia, Chiara Macchiavello. And by the way, if there is any interest in this direction, you know, you can just either talk to any one of us, or there is a website, qt.eu, where I proudly have the shortest email address of the universe, which is t@qt.eu. Okay, parenthesis closed, and you can get all the information there, okay? And so this is really a very current topic, of course, not for scientific discussion, also for scientific discussion, but with education specialists, yeah, which are very much involved in this. And again, I mean, this is something where Italy is now pushing forward, especially the CNR, but also the university system, of course.
Other questions?
Question from the organic chemistry. So, yes. So you mentioned that molecules are,
yes,
you know, one component of the system, and to create this kind of entangled states. You know? So what are the most promising one that you're considering?
So at the moment, those are the smallest one. They are dipolar molecules, yeah? Potassium, rubidium, you know, small dipolar molecules, and there are experiments, for instance, by our colleague, very prominently, for instance, John Doyle at Harvard University, and Dave DeMille, and other colleagues in that field, which are manipulating those molecules with external lasers and electric fields in order to achieve a coupling and entanglement, which is similar to the one which I described for Rydberg atoms. And the idea is really that, you know, these dipolar molecules, if you use the dipole moment, the quantized dipole moment of the molecule as the qubit degree of freedom, they are very, very stable. And so they provide a lot of advantages. But this is not the only connection between organic chemistry, molecular physics, and quantum technology, because, of course, a quantum simulator is very well suited for developing understanding of complex materials, such as many body, many spin systems, but also complex molecules. And one of the long-term perspectives that we are considering is also development of new chemicals, new drugs. And in fact, such companies as Bayer, BASF, and I mean, next week, Tuesday, I have to go to Covestro, which is one former branch of Bayer, in Leverkusen, in order to discuss applications of quantum simulation, because they want to set up a team. And I cannot even say more because I had to sign an NDA, a non-disclosure agreement with them, because they really mean serious business on this. But this is more the side of application of quantum technology to organic chemistry.
Some other questions?
I spoke too much.
Okay. So in this case, we thank the speaker again. Thank Tommaso again.